Is it recorded? Recording? Yes. Okay, wait. Okay. Good morning, class. Today we will have a look on how to use the member stiffness matrix in the stiffness method. Okay, so please refer to this appendix, the stiffness method resource that I have shared to you before. Okay, and have a look. Okay, on this 3 pages document. If you can see that there is for truss structures, there are these some of the matrices here. Okay, we are going to apply this today. So you have a K prime, T, okay, and then K, and you can see that they are so this parameter Cx, Cy. Okay, what is this about? Okay, we are going to talk about this today. And for beam, okay, so if you can see that we have this K prime same as this K. Okay, so and then for frame structures we have this K prime, T, and again the K. Okay, so Cx and Cy also the formula is given to you, but I will show you the other formula, okay, how to obtain the Cx and Cy today. Okay, so before we go on this topic, okay, so I would like to quickly, okay, go through what we have learned, okay, last lesson, okay, on the stiffness method. So I'm going back to my slide. So get ready with this appendix, okay, so that you can refer all the time these matrices, okay. So let's go back to what we have learned last lesson. Okay, I start with this learning outcome. Okay. So we have learned how to identify the constraint and unconstrained degree of freedom last lesson, okay, where you actually at the end you determine the vector of D, okay. So we also determine the vector for Q and vector for Q naught. Okay, Q is basically deal with this applied loading or the support reaction, and this is talking about at the nodes. And then you also determine the vector of Q naught, okay, where you actually determine the fixed end reactions due to this intermediate loading. Okay, whenever elements has the loading, okay, so you find the fixed end reaction at the nodes. Okay, so you determine the vector of Q naught. Okay, so today we are going to have a look on how to use this member stiffness matrix and what is this transformation matrix. And we have two. One is the displacement and another one is the force. Okay, so this is the T, okay, for all these structures. Okay, so we don't specifically talk about the composite structure because we're going to combine the application for the truss and beam, okay, together. Okay, let's have a look what we have learned last lesson. Okay, we will talk about the procedure of the analysis. Okay, so we have actually prepared ourselves for the analysis. Okay, and today we are going to look at this item 2 and item 3. How to construct member stiffness matrix and how to construct structure stiffness matrix. Okay, I will directly show you this step 2 and 3 for the structure for truss and for beam and for the frame. Okay, so so we have learned last week on where to put a knot, how to identify the elements, and also draw an arrow. Okay, this arrow to indicate where is the near end and where is the far end. Okay, so Then we talk about the global and local axis. Okay, you need to know when I talk about local axis, you are referring to which axis. Okay. Then we are also talking about the DOF. Okay, so remember again a truss. There will be 2 DOF per knot. Okay, like this. This one. Okay. Horizontal and the vertical. Okay, what we have drawn here is a positive sign. And for beam, there are also 2 degrees of freedom per knot unless there is an axial effect in the beam. Okay, so we talk about the vertical, okay, and the rotational. Okay, and then for frame, there are 3 DOF per knot, which are horizontal, vertical, and also rotational. This is for 2D structure. Okay. So we also know that this DOF must be indicated in all the knots. Okay, if you have 4 knots, so you need to put this DOF, okay, this indication or in terms of arrow, okay, in all the knots. Okay, then you need to give a number to it. Okay, and we have a rules. Okay, so this is our rules. We label the unknown displacement first, then we label the known displacements. Okay, so this is our first lesson outcome. So you need to know which one is the unknown and which one is the known displacement. And the easiest guideline is whenever have a support reaction, we know the displacement as equal to 0 unless they are support displacement. Okay, so the other which is not deal with the support reactions, they are all unknown. Okay, unless it is given to you, you know the displacement. Okay, if not, we need to determine it. So we have learned how to get this vector of D, vector of Q. Remember the size of the vector depend on your number of DOF. So if you have 8 number of DOF, so you have D1 until D8. And then one thing that we have learned also, we learned that if you have an unknown D, okay, so you will have unknown Q at the opposite. One is at the top and the other is at the bottom. So you can always recheck on this. And then Q will be also liaised with these loadings at node. Okay, so then we also learn about the intermediate loading. Okay, so which is deal with the Q node. Okay, remember there is a statement that the beam or any elements must be free from the loading along its length. Therefore, any loading UDL in terms of rectangular, triangular, point load, okay, more loadings. So you don't want to create nodes in between because they will makes your this computational time become complicated and long. Okay, if you are using this especially manual calculation. Therefore, you allowed a treatment, so-called Q node, okay, to to actually clear this loading, okay, from your element. Okay, what you do is actually you find the fixed end reaction due to this loading. Okay, then this fixed end reaction due to the loading will be considered as Q node. Okay, so again, you determine also for your Q node vectors. Okay, so now you have also practices on these several of these problems. Okay, and today we are going to look at member stiffness matrix and also structural stiffness matrix. Okay, we are going to have some reading, okay, quickly on this, but I will share you a link later for a document on how to derive this stiffness matrix if you are interested. Okay, but in our syllabus, we are more on the application. okay, of this member stiffness matrix that has been derived. Okay, so but you can keep the reference that I have shown you if you are, going for advanced level, or you are very interested in what is this input in this matrix about. Okay, so you can have a look on that. Okay, so let's have a look on this. We are going to look at beam, okay, here. Okay, so if you look at this, and this is an element, beam element, okay, and it has a constant cross-sectional area, okay, and then we are referring to the local axis, where the x is always parallel with these members, and you have a y prime. Okay, so now we are talking about the some inputs at the end, okay, at the near end and also at the far end. Okay, so if you look at here, the linear and angular displacement associated with these loadings also follow the same sign convention. Okay, we already draw the DOF. If you remember, the DOF for the beam is vertical and also rotational. Okay, so they are all drawn in the positive sign. Okay, so when you talk about the displacement, here we also talk about using this positive sign, okay, according to this arrow. Then we will impose each of these displacements separately and then determine the loading acting on the member caused by each displacement. Okay, let's have a look on how. So for example, in this beam member stiffness matrix, we have dealing with two DOF, the Y displacement and another is the Z prime displacement. Okay, so now let's look at the Y prime displacement. So Y prime means that the displacement at this direction. So what the strategy used in the derivation is, okay, so they allow, okay, a positive displacement d and y at one of the end, while the other possible displacement are prevented. So if you see this, it should be at the fixed condition of this element, but now at let's say this is near end, okay, they release, okay, and make this y prime displacement possible. Okay, so means that they allow this y displacement, and they calculate the associated shear force and bending moment. Okay, they're acting at the near end and also the far end. You can use many methods to get this answer. For example, slope deflection method, virtual work method. Okay, but it will be a long calculation if you are doing. You have tried it, right? So, but the concept is you are releasing the y displacement, and you get the shear force and bending moment at the end, and you go to release another end, far end y direction displacement, and again you get the resulting shear forces and bending moments, okay, at the ends. Okay, so then you continue with the Z, okay, direction. So right now for Z direction, or we call a rotation, okay, so we also release that, so it will be look like this one. So now you allow, initially it is fixed, okay, so you allow it has a rotation here, then you calculate the resulting this shear force and bending moment at the ends. Okay, if you can see that this Q is the shear force, okay, this Q and Z will be the moments. Okay, they are derived in terms of this Z rotation, okay, D and Z. Okay, so then we are going to gather all this information, okay, that we have derived here, and putting in this matrix. Okay, if you can see that we have information in the derivation is the Q, okay, and some of these parameters 6EI over L squared. And then we have a D. Okay, if you can see that this is a force and the displacement relations. And this 6EI over L squared, the information we call a member stiffness matrix, K. Okay, so when we gather it, it becomes a big, a complete relations. Okay, we gather all the information, like for example, the Q and Y. Okay, Q and Z. So what is the Q and Y? Okay, N is a near. Okay, Y is a Y direction when you release. Allow the near end to have this Y displacement, and Q and Z you can determine earlier when you have actually allowed a rotation at the near end. Okay, and this QFY will be talking about when you are releasing the Y displacement at the far end nodes. Okay, and QFZ is what you have releasing the rotation displacement at the far end. So now you are actually gathering the informations that you have derived from the ends, okay, to put in this matrix. Okay, that is why you get all these 6EI, 12EI, all these so-called, we call a K. Okay, this is member stiffness matrix. This equation 15.2 is only for a member or for an element. Okay, because we are deriving these relations between the near end and far end, the reaction, the forces with the displacements. Okay, this is what happening in stiffness method. We want to know what is the relations between the force and the displacement. Okay, so these equations will be used. Q equal to KD, and the K will be this one. Okay, today we are going to use how to use this to determine our member stiffness matrix. Okay. So once all the member stiffness matrices have been found, we must assemble them into a structural stiffness matrix. Okay, so K. Okay, and the row and column for each K matrix, equations 15.1. Okay, this one I will show you in the practical matrix later. Okay, but what I would like to highlight is, if you have 5 member stiffness matrix, if you have 5 member or 5 elements, you are going to determine this 5 times, unless the member have the same information. Okay, so you need to determine this for 5 times unless they are same information. Like for example, the EI is the same, the length are the same, so you may maintain. Like for example, member 1 and member 2 are the same, then K1 for K2 are the same. Okay, so this is deal with element. Okay, so then once all these member stiffness matrices have been found, we need to assemble them into a structural stiffness matrix, because we want to solve actually at the global. We don't want to solve element by element. Okay, so we need to gather them into a structural form. Means that for an entire structure. Okay, so then let us have a look. Okay, so maybe this will be okay. So here, this is if you can see that now the relation is still it looks as it shown earlier, Q equal to KD, right? But they are all in the capital form. Okay, this is just to differentiate that these now are at the structural level. Okay, just now the small q equal to small k's and the d are all about local. Okay, but now we are talking about the global. Okay, so global or structural level, you can actually partitioning the stiffness matrix into the known and unknown element of load and displacement. If you have follow the rules that I have shown you in earlier class, where the displacement, okay, the DOF, you number it the unknown first, then the non-displacement, you will, you will eventually come to this step. Okay, you will finally come to this step where you can partitioning. Partitioning here means that you put, if you are in an office, okay, you visit an office with the partitions. So these dotted line are actually the partition, okay, for these uh, uh, inputs in this matrix. Okay, you can actually put a very big matrix, a partition. Okay, how, where to put a partition? Okay, as we have shown earlier, I wish to go back to this a bit. Wait. Okay, so if you still remember, we have already learned partition earlier. If you can see that, we have given the partition here where the D 1 to 4 is actually, can I write, D unknown. Okay, this is D known, and this is Q known, and this is Q unknown. Okay, if you can see that these unknown are actually opposite placing. Okay, so now let's go back to our okay, later you will see that your relations can be partitioned in such. Just now the unknown is at the bottom, right? And the displacement unknown is at the top. Okay, and the non-displacement at the bottom, and the Q is at the top. Okay, so once you apply these partitions, okay, so this K11, K12, K21, K22 will you can also apply and partition, okay, to make you easier in your solving. You will realize that, can I see? Okay, it is in different page. Okay, you will realize that if you want to solve for this unknown displacement, okay, you can apply these equations. Q1 equal to K11 multiply DUK plus K12 multiply DK. It's like this. Okay, the matrix formulation. Okay, I repeat. To get this equation to 15.3 is QK equal to K11D unknown plus K12D known. So how you do that? You are actually putting the first equations here. QK equal to K11, okay, multiply with this. Okay, then you plus, I put a square, okay, K12 multiply with DK. Okay, you plus it. So this is how you do your matrix. Okay, so for those who forget about the matrix, the calculations, you need to go back to do a slight revision. But here is sufficient for you to know. Okay, in order to get this first equation. Okay, QK will be equal to K11 multiply DUK plus K12 multiply with the DK. Similarly, for the second equation, okay, QUK will be K21, should I put circle again? Q21 multiplied with DUK plus, okay, K22 multiply with decay. Okay. So once you have gathered all these equations, you solve for this simultaneous equation. Then you can solve for the unknown first. In these equations, you solve for the unknowns. Once you solve for the unknown, then you can solve for the Q unknown. Okay, this is the process. Okay, but I don't think we will come to solving the matrix today. We are just want to determine the K11, K12, K21, K22. What is that? Okay. All right. I have to show you the frame member stiffness matrix. If you look at the appendix, go to the frame. Okay, so member stiffness matrix in this appendix, we use K prime. K prime is member stiffness matrix. In this appendix, they might have different symbol, okay, in your other references. Okay, so I'm going to use this as the I mean, how to say, main source to tell you the key prime for beam and also key prime for thrust. Okay, it is all here. Okay, so if you look at this, okay, so now what is the nx prime, ny prime, nz prime, fx prime, xy prime, fz prime? Okay, so we are actually talking about the DOF. If you remember, if this is element 1, okay, if this is an arrow, okay, so you have a node, let's say this is node 1, let's say this is node 2, okay, let's say for a frame, we have 3 DOF, okay, which is, sorry, horizontal, vertical, and also rotation. So you need to put this DOF here, okay, at the nodes, at the near end and also the far end. So then if you want to know what is this about, so this can be named as the horizontal at the near end, okay, at the Y direction at the near end, and the Z rotation at the near end. And similarly, you will have at the far end, at X direction, at Y direction, and also at Z direction. So you can talk it, I mean, you can tell in terms of displacement or forces. Okay, so I'm talking about this direction here. Okay, so now if you look at this matrix, you will find that you will have the same and x prime and x prime for the first row and first column, and ny prime and y prime for the second column and second row, and z and so on. Okay, so if you want to simplify this whole thing into the member stiffness matrix, okay, it is actually you need to refer to beam. What is the DOF for the beam? Okay, so let us just draw, okay, before we go to the, but I don't have place. Maybe can I draw it here? Okay, so let's say this is beam. So remember, in the beam, the DOF, there are two. One is the vertical and one is the rotation. So if you want to draw it here, so this will be N Y prime and N Z prime. Okay, but you don't need to draw this, I mean, every time. This is just to tell you, okay, what is this about. This is at the far end, Y direction, and this is at the far end, Z direction. So for beam, you are dealing with this NY prime, NZ prime, FY prime, FZ prime only. So nx prime, fx prime, you don't use it because you do not have that direction of the DOF or that forces at that direction. So once you eliminate that, you will quickly find this template, okay, or this is the member stiffness matrix for your beam. If you refer back to this appendix, if you go to the K prime, is the member stiffness matrix. This is actually an input extracted from the frame. Okay, so you need to be aware on that. I mean, in case it's, I mean, you don't have this resource, at least you have one resource, then you can extract the info, okay, from this frame for truss and also for this beam. Okay, so let's see how to extract it for truss. So for truss, we only have axial effect. This truss, we only have axial effect. Okay, we don't have any the perpendicular. So therefore, I don't draw it here. It will be dealing with only x parallel, the forces parallel with this member. So you will be talking about nx, fx, this one, the one that have been eliminated. Okay, so if I circle them, okay, so then you will see that in your appendix, this will be the one that we want to use. Okay, so if you can see that they have simplified it and put this AE over L extracted outside the matrix. Okay, because they are constant. Okay, if it is not constant, then you need to, yeah, it will be constant for the element. Okay, so this is how what I have introduced you the member stiffness matrix to be used, okay, for truss, for beam, and for frame. Okay, but now how to use them? Okay, so let's have a look. Okay, so okay, I will start with an example, but I will just touch on the member stiffness matrix. Okay, so for example, this example, I have sent you a compiled version of few examples. So this example also one of in the beam. Okay, you can also refer that. Okay, if you cannot see it here, I'm talking about example 1 of the beam. Okay, so now I want to go to the member stiffness matrix. Okay, so how to use this template to determine the member stiffness matrix? If I go back to the problem, okay, maybe here. Okay, so we have identified a class. Do you have any question to ask before I proceed to the application?
No.
All right. So now I'm referring to example on the beam to show you how to use the member stiffness matrix. Okay, but we need to understand the problem first. Okay, so where are the nodes? The nodes happening at A, B, and C, element 1 and 2, and the arrow drawn, okay, and we have this, let's see, the DOF is that numbered correctly, okay. So we have a support reaction, 3 support reaction at A, right? So 3 and 4 will be known or unknown, class?
No.
Yes. We know that the displacement is equal to 0. Okay, for number 3 and number 4. Okay, let's move to B. Okay, 5 and 2. Okay, which one is non-value?
5.
5, yes. 5 because we have by, so 5 also restrain, a constraint, okay, at that direction. So 5, the displacement is equal to 0. So 2 is unknown. Similarly, at C, 1 is unknown. Therefore, we can name the unknown first. So 1, 2, and the rest, you just name it accordingly. 3, 4, 5, 6 will be equal to 0. Okay, so this is a bit not complete. Let me, what is this? I remember this is 5. This is 2. Okay. Okay, this is the numbering of the DOF. So what you need to do is you refer to the, because this is beam, so you just refer to the beam template. Okay, so make sure you get it correctly. You go to the appendix, go to the beam structure, and if you can see that, you are referring to this. Okay. Okay, K prime. So now in this case, I will highlight to you, many are actually repeated. So we have 12 EI over L squared. We have 6 EI over L squared. We have 4 EI over L. And we have 2 EI over L. We have actually 4 inputs that you need to determine only. The remaining are just repeated. Okay, like for example, at this K11, you have this 12 EI over L cubed. But at K13, you have negative 12 EI over L cubed. So you no need to determine again 12 EI over L cubed for so many times. You just put the K11 to K13 and apply a negative in front. Okay, therefore in this case, so if you can see that this is what we are doing. We are selecting this 12 EI, 6 EI, 4 EI, and 2 EI over L. Okay, to calculate what is this. So you need to know what is the E and what is the I. If not, it will be in terms of EI. Okay, and what is the L, the length for this element. Now you're talking about this element 1 only. You don't talk about other element. Okay, so for this element, you need to draw this element and see this all the information. Okay, so you can do it similar for your Q naught as well. There is no problem. Okay, so now you have get this all this input 6 EI over L squared. Okay, 4 EI over L. Okay, 2 EI over L. Okay, once you have solved for this, you just put it into your template. Okay, how you do that? You need to name this member stiffness matrix first. K. Okay, K I. So element 1, you put number 1, K1. Okay, so let's start. 12, the first one, K11 is 12 EI over L cubed, is 2,400. So this K11, you just put 2,400. Okay, then you go and find which are the the same input, like K13. Okay, negative. Okay, then what else? You see there's K31. Okay, you put it negative. Okay, K33. Okay, you put it. So that's all. Then you go to put this information on the 6 EI over L squared. So it is acting at the K12, K14. So you just put in 7,200, putting into this specific location. So you search for more location and you just put it in. So once you complete this, this is a repetitive work, and it is very easy to cause error if you are doing manually. Okay, so be careful. Okay, the next thing I would like to highlight is this. If you can see this, okay, this is a numbering for n, y prime, n z prime, f y prime, f z prime. So you are actually talking about the near end to the far end, okay, direction. Okay, so it's you have a y first, then z. So how you get this value? You go to your information. Okay, now you see that number 4 is actually your vertical y at the near end information, and then 3 is the rotation. So you have 4 and 3. Then you name at the far end the vertical first, 5 and 2. So you name at the far end YZ as 5 and 2. Similarly for the vertical, the vertical numbering, you just put it the same, 4, 3, 5, 2, exactly like the horizontal, the columns meaning. Okay, class, do you understand what I'm trying to do?
Yes.
Yes, madam.
Okay, so actually, I think I spent too much time. Actually, you just refer to the template. Okay, find the inputs, and then there are only 4 difference in this beam matrix. Then you just put it. Calculate it. Just put it in the template, and then you need to number uh, the DOF. Okay, for this element from the near end to the far end. Okay, so you do it as the same for the member 2. Okay, member 2, this is numbering is 5, this is 2, and numbering of the DOF, this is 6, and this is 1. Okay, so now your difference, the element, the inputs are different is because you have the length 2 meter. So you need to repeat calculating this 12 EI over L cubed, 6 EI, 4 EI, 2 EI. And if the EI are different from element 2, so you need to adjust on the EI as well. Okay, so once you get this, you plug it into this template. Okay, remember now you are at K2 and you name this numbering. This numbering is very important because we will use this for the structure matrix. Okay, one thing is to be highlight here. If you can see that I'm drawing this line. Oh, not straight. So this triangle, this input is actually mirror to the bottom triangle. Okay, if you can see that, I highlight some for you to see. Okay, they are mirror. So actually, you no need to find, you just find the top triangle. Okay, will do. Okay, because they are mirror. Okay, so now I want to show you how to construct structural matrix. I'm putting this member stiffness matrix K1, K2 here. Okay, and I have named the DOF. Okay, for the number here. So now when I want to form the structure matrix, the size of this matrix will be the size of my total number of DOF. My number of DOF is 6 in this case. Okay, there are 6 DOF because I have 3 nodes. So if you can see that, I'm up to 6. So now I want to write this matrix, how to do it. Okay, I will show you, you need to combine it. Just sum out K1 and K2. That's all. Okay, how to do that? Okay, let us try on the one that I highlight in blue. Okay, so I want to find this information, K22, or column number 2 and row number 2. Or let's say this is column, okay, number 2, and this is row number 2. So I want to find column number 2, row number 2. So I go to K1 and search any column number 2. Yes. Row number 2, yes. So I highlight in the blue box. Okay, then I go to K2, I search for the column number 2 and row number 2. Okay, I highlight in this, if you can see that. Of course, you don't need to highlight in your calculation, but I'm highlighting here so that you can see it more clearly. So you just plus it, sum this two information, you will get this, K22. Okay, let us find for another one. Okay, let us find for this K16. Okay, or column number 6, row number 1. So I go to find column number 6 here. Oops, there are no column number 6 at K1. So I go to K2, or there is a column number 6. Okay, then row number 1. Okay, so the one I highlighted in red will be the answer for K16. Okay, to make sure you understand, can I have you to find what is key 5? Can you find this? Can you try? I give you 2 minutes, okay, to try whether you can get key 5. Okay, for those act very fast, you may try on several more, okay. Okay, can you get it?
Yes, madam.
Yes.
Okay, so I've also just shared to you if you want to know the derivation, okay, for this stiffness matrix. So now for the beam member stiffness matrix and structure stiffness matrix, yeah, the process is just like that. Okay, so I would like to take 5 minutes break. Then we will continue to see what is the difference between the for the truss and frame. Okay, analysis. Okay, so I will check the attendance right now. Okay. Do we have Aina, my Sarah here? Aina?
Yes, madam.
Okay, can you take your attendance? Huh? Check. Do we have Zwani, Siti Zwani here?
Yes, madam.
Yeah, can you help to take your attendance?
Okay.
All right. Okay, so if you can see that I have also posted a lesson plan, the updated one with the latest date of the test. Okay, please, uh, yeah, be aware on that. Okay, let us have a break. Can I start from now, the 5 minutes? Then we'll continue with this. Okay, frame and trust. Okay. Okay, class, can we come back?
Can, madam.
Okay, yeah. So actually, if you found that we have spent quite some time on how to understanding on the member stiffness metrics. Actually, if you want to apply that, there is not a difficult uh, things. Okay, it's just to pop into the template and we determine it. Okay, similarly for this trust. Okay, so of course I will still share with you so that you understand what is this behind. Okay, so it might be a bit lengthy. Okay, but you can always refer to the notes. Okay, if you miss out some of this important this concept. Okay, so still again once I brief on this concepts of what is behind of this key, the application of the key is not yeah, it's just to put in the template. Okay, so again I crop this from the appendix just now. I would like to highlight that key prime in that appendix, okay, is the member local stiffness matrix. Okay, so it might not be in my notes. Okay, but this the one highlight in the box is the member local stiffness matrix. So yeah, just now we are talking about the what is the forces or what are the displacement at the end of member beam member. But now if you look at the truss member, we are talking about only along the member, which is the your axial force or the displacement, elongation or shortening. So it will be along x prime only. Okay, so of course, at the end later, we are dealing also at y direction, okay, of the displacement. Okay, but in terms of forces, we are talking, if it is at local, we are talking at the axial effect, okay, x prime. So now there are a few forces that will be developed, okay, at the near end and far end, okay, yeah, similarly like in the beam. So I will not getting very details here. You can have a reading, okay, but this page shows the end in derivation or development of the end forces with regards to the displacement, okay, at the near end and also at the far end. So then a load displacement equations can be written, okay, as such. So you have this end forces and the end displacement, and you have a key prime or your this members stiffness matrix. Okay, so this is very you have seen this in the beam derivation for the beam earlier. Okay, where Q is equal to K prime D. Okay, so K prime for the truss is AE over L, and yeah, dealing with this matrix. Okay, 1 minus 1 minus 1 1. Okay, so then so what is the displacement transformation matrix? Okay, just now we said we want to talk about displacement and also the force transformation matrix. So now if you look at that, we have a x prime, y prime, and we also has the x and y, missing y here. Okay, so we have a local and also global coordinates. And the one drawn is all the positive sign. So now we want to convert, okay, the local to global. Okay, so you are going to look at the transformation matrices, and there will be some, there will be a new terms that you need to learn here, which is called directional cosine. Okay, directional cosine is talking about this angle. We cosine this angle, theta x and theta y. Okay, if you look at the previous page here, you have this theta x and theta y. Okay, so because now we want to develop a method for transforming the member force Q and displacement D defined in local. Now we want to change it to global. Okay, what about the Q happening at the local? How to change it to global? Okay, we don't do so for the beam because beam is aligned the local axis and the global axis, they actually meet. So you no need to change the local to global. Okay, they are the same. The local and the global coordinates are the same. Okay, in this beam. So, but we need to do that for truss and frame because we have some elements that is not. Okay, the x prime is not meeting the x. Okay, so that is why derive for this transformation matrix. Okay, so now the directional cosine, if you want to define, yeah, it will be these equations will be the definition for the directional cosine. You need to find the lambda x, which is dealing with cos theta x, or lambda y, which is the cos theta y. So this theta x and theta y will be referring to your element. Let's say this one. Okay, if you look at this element, this arrow means that you have a near end and you have a far end. Okay, so the theta x will be response to this angle to the x global x axis, and theta y will be the angles of these elements to the vertical, the y, okay, axis. Okay, so if the arrow is going oppositely, so you have a negative value for this. Okay, so this cos theta x, cos theta y, you can use this formula, or using this, I will normally use this equation. Uh, uh, x at the far end minus x at the near end divided by the length. Or y at the far end minus y at the near end divided by the length. It will be the lambda y. Okay, so far end minus near end divided by the length. So you get the lambda. Okay, so we are going to practice this later. So then now this page tells the concept of how to change, I mean, this local to global. Okay, what is the relationship between the local and the global displacement? Okay, so from this figure, okay, they have derived that the relationship is the local d, small d, with the global d, okay, you can use the lambda x and lambda y, okay, to get this, I mean, the relationship means that dn is actually equal to lambda x multiply d and x, big D, okay, plus lambda y multiply the big D and y, okay. So then you can also similarly getting the far end, okay, the relations between the displacement at local and the global, okay. So if you put it in the matrix, okay, you will see that you have this local, okay, this is the displacement transformation matrix, okay, multiply with the global, okay. Means that once you solve for the, we normally solve for the unknown displacement, and that unknown displacement is at the global coordinates, okay. But now if you want to find the elongation or shortening, that is not at the global coordinates, that is at the local. So if you would like to know that local displacement, you need to use this equation, okay, to determine the local from the one that you have solved, the global displacement. So this T now, to introduce you, the name is the displacement transformation matrix, and it consists only lambda x and lambda y. Okay, so you need to know when you want to use the T. Okay, so here I give you an equation 8, okay, to remember. Okay, these equations will not be given to you. Okay, only given to you the T, the D. So you need to know how to use this matrix. Okay. So then we talk about the force transformation matrix. So now the force transformation matrix means that, again, when we analyze that, we solve for the global forces, the global support reactions. But if you want to find the internal forces, like in truss is the axial force, okay, in the frame is the shear force, axial force, and the bending moment for that particular element. So we need a force transformation matrix. Okay, similarly, this slide explains the relationship between the global and also the local, the big Q and the small q, and they are related with the lambda, okay, cos theta x and also cos theta y. Now, if you look at this matrix form, okay, it will be in Q equal to T transpose Q. Okay, so these T are the same with this T actually. Okay? They are lambda x, lambda y, lambda x, lambda y, and with zero, okay, information. And now we transpose this T. Okay, write it in the transpose way, vertical. Okay, so you get this. Okay, lambda x, lambda y, lambda x, lambda y. So this T transpose is also named force transformation matrix. When we will use this, when we want to change these global forces, okay, into the local forces, we use this transformation transpose transpose T, okay, or force transformation matrix. Okay, so now I have introduced you what is T. Okay, in easy way, the T, the transformation matrix, it is actually act as the matrix to change the global information to the local information, or vice versa. Okay, so please tick in your notes these two metrics. Okay, I mean these two equations. Okay, so now member global stiffness matrix. Now we know that the K prime, and we also know, just now we know, sorry, the local stiffness matrix and the force transformation. This is displacement transformation matrix, and we can transpose it, become a force transformation matrix. And now we want to know member global stiffness matrix. Okay, this is the one that we are going to use. Okay, member global stiffness matrix. Okay, how to get this? Okay, so there are a few equations to come to this K. Okay, this is just to tell you the derivation, but in fact, you don't need to derive in your during your test. You can just apply this K. Okay, this K will be used to determine the member stiffness matrix. Okay, now everything is in global when we want to solve for the displacement. Okay, in stiffness matrix. So how to get that this equation 15? Okay, so let's go to this equation 12. How to derive this equation 12? It is from our previous equation 8 and equation 3. If you still remember, we have transformation from local, small d, to global d. We use the t, d equal to transformation t. This is in equation 8. And we also learn on the relationship between the forces and the displacement at an element, which we have learned in the equation 3 earlier, this equation. So now we put this d, okay, substitute this equation 8 into this equation 3. What we will get? We will get equation 12. How? This small d is actually td. So just substitute it into this equation 3. Then you get Q equal to K prime TD. Okay, so now you get this equation 12. Then how to get this equation 13? Okay, please refer to this equations 11. Okay, this equation 11 is what I have explained earlier, where we actually convert the global, relate the global force with the local force, okay, with the transformation matrix, force transformation matrix. Okay, so now let us putting this k prime. Sorry, this substitute this equation 12 into this equation 11. So this small q right now is k prime td. Let us substitute this into here, the q here. So once this k prime td has been putting in the q, small q, now the big Q become t transpose k prime td. Okay, then we have equation 13. Or we want to make it more easier, this k, we put this t transpose k prime t. We define it as k. Okay, then it become more easier now. Q equal to kd. So this K will be the member stiffness matrix at global. Okay, so how to get this? This K will be T transpose K prime T. Okay, do I have anything here? I don't put it in here. So T transpose is in the, but maybe I will show you again. T transpose is the vertical placement of this T. Okay, so and then multiply with the K prime. K prime is this one. And multiply with this T and this T. Okay, so if you are interested with that, you can try it. So meaning that this T transpose matrix multiply K prime matrix multiply T, you will get this matrix, which is member global stiffness matrix. Okay, and we are going to use this, okay, in our calculation. Are you okay, class? So in brief, if you want to solve this stiffness matrix, firstly, for the truss, we need to determine this K, okay, for the member. Okay, so let's try on one of the example, how to get this. Okay, so this example. Okay, so we have two members here. We're going to try on these two members. Okay, so now these two members, let us this Cx is the lambda x. Okay. Okay, but never mind. We are going to use this Cx, okay, in our symbol. Okay, so let us try to put in the coordinates for this truss. So you can start your coordinate anyway. Okay, let's say 0, 0. Then this would be 3, 0. And this would be 3, 4. Okay, so now in this member stiffness matrix, we only need Cx, Cy, right? But after you determine the Cx and Cy, you will see that you need Cx squared, Cx Cy, and Cy squared. Okay, so meaning that you need to determine Cx, Cy, Cx squared, Cy squared, Cx, Cy. Okay, so Cx is, as we have give you the formula early, is as actually cos theta x. Okay, or I will show you here is the x at the far end minus x at the near end divided by the length. Okay, so if you look at element 1 right now, okay, so x at the far end will be 3. Okay, 3, and then x coordinate at the near end is 0. So minus 0. And the length is 3 meter. So Cx is 1. Okay, so Cy is cos theta y. Okay, or you want to use this YF minus YN divided by the length. So YF is 0. YN is 0. So it is 0. Okay. Are you okay, class?
Yes,
Okay.
madam.
Okay. Okay, so now if you want to use this theta x, I mean cos theta x, this theta x is 0. Okay, so this theta y is 90 degree. Okay, so if you want to use this cos theta x, okay, or because I prefer to use coordinate, okay, so you can use both in both way. So once you have determined the cx, cy, okay, cx is 1, cy is 0, so cx squared is 1, cy squared is 0, so cx, cy will be multiply cy and cy will be 0. So what you need to do is just to put in everything into this template. So cx squared will be, so it starts with cx squared. So cx squared is 1. So you put in 1. And cx, cy is 0. So you put in 0. And so on, you fill in this. And again, you can know that the upper triangle is actually mirror. Okay, mirror. These are mirror line. Okay, you can do only top triangle will do. Okay, if you want to put in the length, if the length for all is different, so you will need to put this length into the matrix. So you become this. Okay, so then you need to number this DOF 1, 2, 3, 4. How to do that? So you go to this, it will be N, this will be N, X, N, Y. This will be Fx, and this will be Fy. Okay, so we refer to this 1, 2, 3, 4. Okay, so this is how you do your member stiffness matrix. And what you are doing here is global. You are not doing the local stiffness matrix. So you can try on this element number 2. I give you maybe 2 minutes, okay, to try on this Cx and Cy. Okay, let me copy back the coordinate. This is 0, 0. This is 3, 0. This is 3, 4. Okay. For now, this is element 2. This will be theta x, and this is theta y. Okay. So you can use cos theta x, cos theta y, or you want to use the coordinate. Okay. You can put it here. Okay, please have try. Okay, class? Any question?
Okay.
You can get CX and CY, is it?
Yes.
Okay, so of course, after this class, you can try more. Okay, but how to get the CX and CY is very important. Okay, in this trust member stiffness matrix. Can I continue? Class?
I can, madam.
Okay, so I would like to show you structure stiffness matrix. Okay, so I think there is no different to get the structure stiffness matrix. Okay. Okay, let us just look at this. Okay, so we have determined the K2. Okay, using the template K1. Oops, okay, my K1 is down here. Okay, there is no problem. Oops, cannot remember. 1, 2, 3, 4, 1, 2, 5, 6. Oh, this is 1, 2, 3, 4. This is 1. Oops, 1, 2, 5, 6. Okay, let us just try a quick one, finding two, maybe two inputs, just to show you. Okay, let's see. Let's try to get this K22. Okay, means that you go to column 2 and row number 2. Okay, so here I have column 2, row number 2, and column 2, row number 2. Okay, I sum these two. Okay, 0.128 plus 0, so I get 0.128. Okay, so maybe I try another one for you. Okay, let's say 1, 2, 3, 4, 5. Okay, this is K15. Okay, means that column number 5, row number 1. Row number 1, column number 5. Okay, so I go to here only. K1, there is no 5 elements of, I mean the column of 5. So I have this one. Okay, so column 5 is here, 5. Okay, so this will be the, oops, wrong. It's not 5, 5. It's column 5. Now I start to do my mistake. Okay, column 5 and row number 1. Okay, this one. Okay, so this is one, my K15. Okay, so this is how you placing your structure stiffness matrix. Okay, and you don't need to place it all. You can place it this top triangle. Okay, will do. Okay, so now I want to tell you about this arrangement. Okay, since we're already here. Okay, remember we are having these relations, the Q. We have determined the, learn how to determine the vector of Q early. Determine the displacement. Okay, and these are the K that we have determined today. Okay, so when you place it, the matrix in such, you can do a partition. Okay, how to partition? To differentiate this unknown, the non-K and unknown Q. How? I will start to draw. Oh, I hope it is. Okay, and then if there are 2 row only, so here I will also stop at 2. So these are my partition where I have this D unknown and this is D known. And I have this K, I consider 1, 1, K, 1, 2, K, 2, 1, K, 2, 2. So if you can see that, I actually have only 2 equations to be solved. Okay, I'll be looking at this. K11 and K12. Remember, to get this, it is actually QK equal to K11 D unknown plus K12 D known. Okay, but this D known is all 0. So whenever these informations here in K12 multiply 0, it will be 0 in this case. Okay, therefore you only left this to solve. Okay, so I will read here. Okay, you will have 2 equations here. One will be it will be okay, so I shall keep my writing just now. Okay, so now this will be the one used, okay, to solve your D1 and D2. So what you can do here is you can write the first equation is AE 0.405 multiply D1 plus 0.096 D2. Okay, so this will be your equation for 1. Remember, you have this K11, K12, K21, K22. Okay, D1 and D2. So you are actually referring to this one, multiply this, and then plus this one, multiply this, and so on to form the first equation. Then you have the second equations, -2, where you are referring to this row now. Okay, so it will be 0.096 D1 plus 0.128 D2. Okay, this will be equation 2. Actually, you have to be continued, but referring to this is all 0. So that is why when 0 multiply 0, this 0 multiply this 0, and this negative 0.096 multiply 0, negative 0.128 multiply 0, you get 0. So once you solve for these 2 simultaneous equations, you solve for D1 and D2. Then from this D1 and D2, you can create another 4 equations using the same method just now. Okay, but now you have the input of D1 and D2. Okay, then you can solve for the support reactions. Okay, so maybe we will go through this in real in our next class. Okay, class, I think today I don't intend to go for the frame member stiffness matrix. I think that's all for today. Okay, you can do a revision again once, referring to my notes to try, okay, your understanding. Okay, so I think I will end today's class. If you have any question, you can ask me. Okay, so I will stop recording as well. Okay, if you don't have any question, yeah, I see you next class. Okay, and maybe I will start with the member stiffness matrix for frame. Then we will start with the start to explore it using example, a full example. Okay. So thank you.
Thank you, madam.
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 Thank you, madam.